Hi everyone, we are back again with other content. So this time we'll be discussing the CPU architecture. So CPU architecture has several underlying topics, but let's start off with a brief introduction to the CPU. So what is CPU? CPU stands for Central Processing Unit, which runs the operating system, and it oftentimes called as the brain of the computer or the spark of life in the modern computer architecture. Next up is a history about our CPU. So before, CPU motherboard contains expansion card slots that has different functionalities. So the slots has minimum of 20 discrete components which now fits in a tiny microprocessor. So this advancement in silicon technology is made possible because of the Moore's law. Moore's law is based on the observed trend showing that we can double the number of transistors per unit area about every 2 years, and this was idealized by Gordon Moore. Next is the history of our computers. So in 1945, it is considered to be the birth of the digital computing. Computers before was fragile, slow, and of large sizes. So the following year, ENIAC or the Electronic Numerical Integrator and Computer was introduced. So vacuum tube technology was used on the earlier computers, which made it huge and unreliable. The programming was also complicated and error-prone, but is still the cutting edge of the technology in late 40s. Next is bug aside. So fun fact, it was used by famous computer pioneer Grace Hopper in 1946. So operators traced an error on Mark II to a moth trapped in a relay, which is then termed as bug. Next is John von Neumann. So John von Neumann popularized a new kind of computer architecture that was simplified design and programming called the von Neumann architecture. So it has 3 separate systems, namely memory, CPU, and input-output interface. So this also introduces a 4-step of instruction cycle: the fetch, decode, execute, and write back. So this architecture is even used in the basic principles of our modern computers. Next up is Robert Noyce. So Robert Noyce, in 1959, he patented the first monolithic integrated circuit which combined multiple transistors in a single silicon chip. Let's have here Intel's timeline. So in 1968, Robert Noyce teamed up with his colleague Gordon Moore to get into the game, founding Intel, which is a short term for Integrated Electronics. In 1971, Intel unveiled the Intel 4004, is a single-chip microprocessor for a calculator market. The following year, Intel 8008 was the first 8-bit microprocessor, and after 2 years, Intel 8080 was released as a successor of Intel 8008. In 1978, Intel 8086, with its x86 instruction set architecture, became the foundation of the modern CPU designs that we still use today. Next is the computing abstraction layers. So, binary system, in order for computers to function, control and data must be represented by numbers in simple on and off states. That's why digital computers uses a number system based on zeros and ones. Next, for the concept of computing abstraction layers. So in simple terms, computing abstraction layers is the separation between layers of complex computing structures. Next up is the instruction set architecture. So it is a set of instructions that defines what kinds of operations can be performed in hardware. It also acts like a sort of bridge between software and hardware. It has several types such as x86, ARM, and MIPS. We have here the microarchitecture. So a microarchitecture is an implementation or specific design of an instruction set architecture. Stages that the microarchitecture takes are referred as the CPU's pipeline. Next up is the pipeline depth and speculation. So in general, the more pipeline stages you have, the faster each stage can run, and the more stages are being done in parallel. We have here speculation as defined. Also, when a microprocessor executes newer instructions than a branch without knowing if the branch is taken or not, it This is referred to as the speculative execution. Next up is the front end. So the main goal of the front end of a CPU pipeline is to ensure that there is always enough instruction available for the back end to execute. Next is the superscalar execution. So first we have to define scalar execution. It is referred to as a single ALU which can do a single execution at a time. Superscalar execution, on the other hand, implements many ALUs which can operate in parallel. Next is the out of order. So in order execution, or the IOE, are the micro operations executed in program order. So executing it in out of order provides the best performance and energy efficiency. And lastly, the backend. So backend takes the micro-ops provided by the front end and determine their dependencies. So the following are the terms used. So this dependency is tracked by a process called register renaming. Next is the reorder buffer, the allocation, and the vectors. So that's the end of our discussion. Thank you for watching.